Good morning to you. Good morning to everybody. Welcome to another exciting morning of Chem 1211 with your host, me, Dr. White. I better get closer to the camera so you can see me. But, anyways, it's showtime. So, before we begin, important announcements. Ooh, we got serious. Remember, on Thursday and Friday, I will be going through the equilibrium problem set. I highly recommend you do that. Also, don't forget, it's approaching quickly the deadline. I think it's May 5th, which is just around the corner. The way this month's been going, this year's been going. It's almost the end of April. It seems like I just had a Zoom New Year's Eve party I went to. Well, that was wild. But anyways, do the extra credit project. Send it to me by email and I'll check it. One of your colleagues just did. I have to get to it. Yesterday, Dr. White got swamped with a lot of things. I was in some meetings where I do consulting, so that took a lot of my time yesterday, but I'll get back on track. The other thing I do want to talk about is labs. A lot of you aren't handing in or up to date with labs. Remember last week I said it was a deadline. Well, I'm going to be super nice because of the environment we're in with COVID-19. And this Saturday, make it 1 p.m., is the firm deadline getting in any late labs. If you're missing labs and you can't download it, email me and I'll send you it. After that, I'm putting in a 0 if you don't have a lab in. So Saturday, and I'll send out an email either today or tomorrow reminding everybody you've had plenty of time. Don't forget there's a lab due this Thursday or Friday. Do it. It's 10 easy points. And again, don't forget, start working on the extra credit project. And finally, don't forget, it's International Chem 112, wrong class school, Chem 1211. Turn on your webcam day and make Dr. White happy. And all of you have, thank you. Another reason Dr. White's happy is yesterday I made my quarterly pilgrimage to Costco. That's a dangerous place for me to walk into. I was pretty good. I only dropped $200, which for me is pretty good. I can go in there and sometimes drop $600, $700, $800 easily, but I only go about 4 or 5 times a year. And I got everything I wanted, and they're always very nice to Costco by my house. And I assume other Costco's are the same. All right, let's get to work. On Monday, I started talking about the Bronsted-Lowry acid and base theory. And I had mentioned the Arrhenius theory and the problem that the Arrhenius theory does not explain acids and bases in non-aqueous solutions, non meaning without aqueous water, and a lot of chemistry. And Dr. White's done a lot of chemistry where you're non-aqueous. And the important thing to come up with a theory is not only do you have to explain what is an acid and base in non-aqueous solutions, but it also should explain exactly what the Arrhenius theory does. And two chemists, Bronsted and Lowry, came up with their acid-base theory, which is still used today. And you should know, what is a Bronsted-Lowry acid? It's a proton donor. And a proton is H+, which is why I've got it in red here. You should know this. And what is a base? A Bronsted-Lowry base is a proton acceptor. And therefore, if I'm a Bronsted-Lowry acid, here's my proton, take it, I'm an acid. If I'm a Bronsted-Lowry base, come on, give me your protons. I'm a base, and you should know that. Proton donor, here, take my proton acid. proton acceptor, give me your protons, a base. Now, when we talk about protons, an important aspect in our daily life is water. And if you have a proton and you react it with water, which it does, it gives you this molecule, which has a special name because it's so important. It's called the hydronium ion, H3O plus. And there's actually a covalent bond. There are 3 bonds to oxygen because oxygen donates one of its electrons. That's why there's a positive charge. Now, this part I just put down to show you if I have an acid HCl, an ammonia, and H3, notice HCl gave ammonia H plus and H4 plus. HCl lost H plus, became Cl minus, and that's an acid base. And in Bronsted-Lowry, this would be our acid, this would be our base. Because notice H plus went to there. Here you have HCl, it's lost H plus, and it's a very tiny, but it's there, Cl minus. And this picked up a hydrogen plus a proton, which is H plus. So you went from 3 to 4, and notice there's a plus sign there. And that's why hydrochloric acid is an acid, and that's why ammonia is a base. Very dangerous compounds, both of those at high concentrations. Now, everybody take a deep breath, and I can watch and see if you're doing it. Let it out. Take a deep breath. I like my hand signs here when I do that. Let it out. Take a deep breath. Let it out. Are you all relaxed? Good. The next concept, students have trouble wrapping their mind around at first. So relax. If you have a little problem, don't get upset. But for some reason, students, when they think about the next concept, their brain goes like this and sort of, which way did they go? Which way did they go? Relax. I'll straighten you out on it. So let's talk about conjugate acids, conjugate base pairs. And by the way, it's Subtle Wednesday. Are those 2 words becoming dreaded words in your vocabulary? But anyways, let's talk about conjugate acid, conjugate base pairs. When you have an acid and base reacting together, the proton transfer doesn't occur at 100% for most acids and bases. And almost all of them, there's an equilibrium. Now, this is why I put chapter 15 before chapter 14, because in the book you would have bought, if you bought the book, they talk about acid-base equilibrium before you know what the heck an equilibrium is. And that's not good. And Dr. White corrected that. And don't forget today's turn on your, oh, everybody's turning on your webcam. Thank you. Oh, I get to see everybody's face. Hi, Danny. Hi, Amber. Everybody else. Oh, I see all your faces. Dr. White's real happy. All right, back to work. Now, this is an acid. Oops. In chemistry, a general acid is depicted by HA. A base, isn't this original, is depicted by the letter B. Now, this is an acid-base equilibrium. This gives up a proton to this to make this and this. Now, what is a conjugate acid-base pair? That's 2 species or compounds that differ by only 1 proton. Again, conjugate acid-base pairs are two species that differ by only one proton. I will never ask you on a test what is a conjugate acid-base pair, but I will ask you to know how to define it in an equilibrium. So let's learn how to do that. If you look at HA, on the other side of the equilibrium, the only thing that's similar is A minus. And going from HA to A minus, it's lost to H plus. So the only difference between HA and A minus is the fact that they differ by a proton. So those are called conjugates. Now, look out, Dr. White's going Technicolor on you. If we look at B and HB plus, what's the difference between those? And the answer is a proton. And things that differ by a proton are called conjugates. Now, again, let me explain. Things that are conjugates, pairs, differ by only one proton. Remember, the word pair means two, in case you forgot. And HA going to A minus or vice versa, the only difference between these two is a proton, and therefore they're called a conjugate pair. B and HB plus are conjugates, and the only difference between B and HB plus is a proton H plus. Oh, I got to look at all those friendly faces out there. Oh my gosh. Thank you, everybody, for turning on your webcam. And those of you who don't, turn on your webcam. Come on, everybody. All right, now, when we talk about conjugate pairs, we have the term conjugate base of an acid. That's the species that remains when an acid loses a proton. And then you have the conjugate acid of a base. That's the species formed when a base accepts a proton. Now, I don't use the full term, most chemists don't. We just call something a conjugate base or a conjugate acid. So conjugate base is what's left after the acid gives up its proton, and a conjugate acid is what's left after a base accepts the proton. Oh, look at the bottom of the slide. It says see board for example. Dr. White's got to get to work. Thumbs up, people. You see my whiteboard. Thank you. All right, let's go back to the example. Give me time while I write this down. In the classroom, you'd be watching me write it on the board. And here I have give the acid base conjugate acid, conjugate base 4, and you have an equilibrium. Now, I also might write, identify the conjugate acid, the acid base, conjugate base for the following. Now, the first thing I like to do, and notice I have them identified XY, WXY, and Z. Now, first thing I'd like to do is identify the conjugates. If you notice, the difference between these two is H plus, so those are conjugates. And here, the difference between those two are conjugates. Now, on the left are the acids and bases, and on the right, by convention, chemists use, are the conjugates, acid or base. So if I look at W going to its conjugate, Y, has it gained or lost a proton or given up a proton? And the answer is it's given up or donated a proton. What's something that donates a proton? An acid. Now, if I look at X, or B, which I'm labeling X to put in this chart down here, when B goes to HB, its conjugate, is it losing a proton or gaining a proton? H plus. And the answer is it's gaining or accepting. Something that accepts a proton is a base. Now, for the right side, these are both conjugates. So I can immediately write that in. And now we look at this and say, going this direction, going from, let's say, Y to W, does A minus gain or lose a proton? Does it donate or accept the proton? And if we look at Y, which is A minus, when it goes to HA, accepts a proton, and that makes it a base. And because it's on the right side, it's a conjugate base. Next, let's look at BH, which I have letter designated Z. When it goes to B, letter designated X, and it goes this way, does it gain or lose a proton? And here it has BH plus, here it says B. It's lost a proton. It's donated a proton. What is something that donates a proton? That's an acid. And that's how you do it. Now, a lot of students have trouble. Those of you who turned off your webcam, turn it back on again, please. Thank you. All right, now, a lot of students have trouble, and I mean trouble saying H plus. What's H plus? I don't know what it is. Here's a pro tip that will help you out. Just count the hydrogens. Does it gain a hydrogen when it's conjugate, or does it lose it? Count the hydrogens, forget about the plus sign for now, and that will get you on the right track. And you can say, thank you, Dr. White. You're welcome. So if we go back here and look at this again, HA to A minus, notice it's lost the hydrogen, something that loses really H plus, but the hydrogen, that makes it an acid because it really gave up a proton, not just a hydrogen. Now, B goes to BH plus, it's gained a hydrogen plus a plus sign, but for you, it's easier going from left to right. B has gained a proton, hydrogen, that makes it a base. Now, going the other way, right to left, A going to its conjugate, HA, remember, conjugate. That's something that is two species that differ by only one proton. But for you, just think of hydrogen. And A minus going to A Does it gain or lose H? And the answer is H, it gains. It accepts, and that makes it a base. It's really a proton, but for students, it's easier to think of, guess what? H plus, or H, I mean. And finally, BH plus, going to its conjugate B, does it gain or lose H? Really H plus, but you can think of it as H. And the answer is it loses or donates a proton. And that makes it an acid. And on the right side, they're always the conjugates. So Y and Z are going to be conjugates. Now, one thing, students, I have a bad habit. Yes, I have a couple of bad habits, but one in teaching is I tend to put an acid first in an equation. That's not convention. That's just Dr. White. And on a test, sometimes I switch this, and students get all upset. They said, well, you've always done acid first. Why isn't that an acid? How can it be a base? Well, it is, and they get upset with me. So remember, there's no order convention which goes first or second in an equation: acid, base, base, acid, conjugate base, or conjugate base, conjugate acid. All right, let's do a Winky Dink. Did I ever talk to you about Winky Dink in here, the cartoon character? When I was a little kid, there was this cartoon. Ooh, a Dr. White story. Hang on, look out. This is a good one. But anyways, when I was a little kid, I love cartoons. I still do to this day, even though the ones today on TV are pretty lame. The ones when I was a kid were really good. But anyways, there was this one TV cartoon program called Winky Dink, and you can see it on YouTube, some of the episodes. And it was sort of like a star creature or guy with a head that looked more like a star. Weird, but yep, it was true. And he had a sidekick, and he'd be on these adventures, and you'd have to help him out. How'd you help him out? Well, you sent in, I think it was 10 cents or a quarter to whatever your parents did, because you were too young to do that. And you get a piece of plastic that you put on the TV screen. This is back when we had TV screens, not LCD screens, or the type of TVs we have now. And they also sent you a grease marker. And during the show, it would say, all right, kids, Winky Dink is stuck in the hold of the ship. Draw a ladder on your screen to help them out. They'd have a dotted line to help them out, and you would, and then you'd erase it, watch more of it, and do help them out. By the way, my best friend at the time, Dickie Gale, I haven't seen Dickie Gale in decades. He moved out of the state. But anyways, he got in trouble big time with his parents. He forgot to put the screen on, the plastic on the TV, and marked up his TV real bad. They weren't happy. But anyways, I'm going to do a Winky Dink. We're going to do things step by step now. All right. Thumbs up, people. Do you see the equation on there? Thank you. All right. What I'd like you to do now only is identify the two pair of conjugates. There are two conjugates on there, two pair, like I did with the line from one to another. Just identify the conjugates. Remember, Dr. White's helpful hint for students: those that differ by one hydrogen are conjugates. Everything else is the same. And thank you for everybody keeping your cameras on. I get to see real people. Oh, good news. I don't see anybody with smoke coming out of their ears yet. Remember, look for difference in one hydrogen, and those are the conjugates. That's all I'm asking you to figure out. All right, looks like everybody's done. I'll give another 10 seconds. All right, let's do it. Now, the question is, what are the conjugates? Now, here's how you can identify them real quick. Notice here I have a nitrogen, here I have a nitrogen. In Z, no nitrogen, so that can't be a conjugate with W. Therefore, these are conjugates. NH4 plus, NH3. If you do the easy way, it's different from one hydrogen. It's really a proton. Now, if we look at X and Z, notice they both have a oxygen, and they only differ by a proton. H plus, or use the easy way, 2 and 3. Now, once you've identified it, I'm going to do this one, then you know I'm going to share and let you have some fun. Let's look at NH4 plus W. When it goes to its conjugate, NH3, ammonia, does it gain or lose a proton? Think of hydrogen H. And the answer is it's lost one or donated, and that makes that an acid. And remember, on the right side, Y and Z are always called the conjugates. Now, if we look at X, when it goes to Z, does it gain or lose a proton? And you can think of this hydrogen. Here it has 2, here it has 3. It's gained a proton. It's accepted a proton. What is a proton acceptor? A base. So that's how we have the acid base going this direction. Now, I hate when I do backspace and it moves the whole screen. But now let's look at going this direction. We go from Y to its conjugate, W. Does it gain or lose a proton? Time's up. It went from 3 to 4. It gained it. So what's something that accepts or gains a proton? That's a base. And because it's on the right side, it's called a conjugate base. And finally, when we go from Z to X, going this way, going from H3O plus to H2O, do you lose or gain a proton? Think of hydrogen. You go from 3 to 2. Oh, we lost one. What's something that donates or loses a proton? It's an acid. And because it's on the right side, it's a conjugate acid. Ooh, what did I just write? Did I get this? I wrote these wrong. Hold on. See what happens when Dr. White's too happy? All right, Y going to W accepts a proton, it's the conjugate base. Sorry about that, everybody. And Z going to X accepts a proton, or no, donates a proton going this way, and that makes it an acid. Not I confused everybody. I'm sorry. Let me do it again to unconfuse you. All right, when W goes to its conjugate Y, it loses a proton or donates it. That makes it an acid. When X goes to its conjugate Z, it accepts a proton, and a proton acceptor is a base. When you go the other direction, Y to W, it accepts a proton. Something that accepts a proton is a base. When it's on the right side of an equilibrium, we call it the conjugate, in this case, base. And finally, H3O goes to H2O. What? Does it gain or lose a proton? Think of H and let's follow the H. And it, guess what? Goes from 3 to 2. It donates or loses it. That makes it an acid. It's on the right side. That makes it a conjugate acid. And it's your turn to do it all by yourself. For the following, label E, F, G, and H, acid, base, conjugate acid, or conjugate base. Ready, set, go. And I get to look at all the smiling faces out there while you're doing that. Or actually the tops of your heads while you're looking down at your piece of paper. And everybody turns on your web camera. Thank you. Those of you who don't, well, thank you for coming, but turn it on. Come on, make Dr. White super happy. For those of you who finish early, please be patient. I try and give everybody time to finish. Come on, finish. All right, I think everybody's done because I'm seeing some people giving me that look. Get to work, Dr. White. So I will. And let's get to work. Now, let's look at what are the conjugates, because that will help you. Notice I have a nitrogen here, but both of these have a nitrogen, but this has two oxygen, this has two oxygen, so they're conjugates. And if you look, the only thing they differ is from H plus. Now, if we look at F, hydrogen cyanide, and G, they both have carbon in it. H doesn't have a carbon, so these are conjugates. Now we have to figure out what's an acid, what's a base, and what's a conjugate. Now, by definition, everything on the right is a conjugate. So immediately I can write down here, abbreviation for conjugate. You don't want to see me misspell conjugate. Dr. White was always the first one down in spelling bee still. But anyways, I haven't been in spelling bee in decades, but I would be. All right, now let's look at going from E to its conjugate H. When we go this way, does NO2 plus gain, accept, or lose, donate a proton? Notice no hydrogens, here one hydrogen. So it is accepted a proton. What is something that is a proton acceptor? And the answer is a base. Now, let's look at F. Again, we're still going this direction. F goes from F, which is hydrogen cyanide, to its conjugate G, cyanide anion. Has it gained or lost a proton? Count hydrogens. One hydrogen, no hydrogen. It's lost one. What's something that loses or donates a proton? It's an acid. Well, we're half done. Now, consider the equilibrium going this direction. When we go from G to its conjugate E, does it, wrong one, I'm sorry, that. When it goes from G to F, and that's why I like putting the lines here, because it stops you from making a mistake I was just about to make. Does G gain or lose a proton? Count hydrogens. No hydrogen, one hydrogen. What's something that accepts a proton? That's a base. And then the last one, H to E. Again, we're looking at going this direction and going from H to E. Do we gain a proton or lose it? Count the hydrogens. 1, 0. We've lost it. What's something that donates or loses a proton? And the answer is an acid, but because it's on the right side, it's a conjugate acid. And that's how you do it. Oh, let's do one more. These are fun. All right. Does everybody see that on your screen? H3PO4, that's phosphoric acid reacting with an H3 ammonia to give the ammonium cation and the phosphate anion. And let me do this. Identify W, X, Y, and Z as acid, base, or conjugate acid or conjugate base. And have some fun. Are you guys having fun? Everybody say, yes, Dr. White. No, you don't have to. Remember, follow the hydrogens. If I were in a class right now, I'd say, if you're done, look up and smile. I'd see all those smiling faces. And I also say, if you want to frown, you can, but that's not fun. All right, I think everybody's done. Let's do this. All right. First thing I like to do is determine the conjugates. What species differ by only one proton? Ooh, there's a phosphorus here and a phosphorus here, knowing why. So these are conjugates. There's nitrogen here, not in Z. So these are conjugates. So now I have the conjugates and I can go ahead and identify acid base, conjugate acid, conjugate base. By definition, the right side is always the conjugates. So I can put this in. Next, I'm going to look at the conjugate pair, H3PO4, phosphoric acid, W, and Z, phosphate anion. And going from W to Z, have you gained or lost a proton? Think of hydrogen, 3 to 2. Oh, I've lost a proton. What's something that loses or donates a proton? And the answer is an acid. Now, I'll look at X. X going this way goes to its conjugate, Y. It has NH3, it goes to NH4 plus. Now gained a proton, but think of H goes from 3 to 4. What is something that gains or accepts a proton? That's a base. Half done. Now let's consider going in this direction. When we go from Y to its conjugate X, going in this direction, Y has NH4 plus, goes to NH3. Did it gain or lose a proton? Think hydrogen, went from 4 to 3. It lost something. What's something that loses or donates a proton? And the answer is an acid. And therefore, Y being on this side is the conjugate acid, because on the right are all the conjugates. And the last one to do is Z going this direction to its conjugate W. Has it gained or lost a proton? Count the hydrogens, 2 to 3. And hopefully all accept it gained a proton. What's something that gains or accepts a proton? A base. And because it's on the right side, it's a conjugate base. And if you notice something I haven't talked about, but now I can, going from an acid, when it goes to the right, it goes to its conjugate base. And a base, when it goes to the right, this way, goes to its conjugate base. They're opposites, acid-base pairs, conjugates. Whoops. And see, it wasn't that bad, was it? Everybody give me a sour face now, but you'll get it. If not, ooh, time for a commercial from Dr. White. Don't forget tonight, I have my office hour. If you have any problems whatsoever dealing with Chem 1211, other things too I might have help, but 1211, stop by and I'll help. Speaking about helping, I was thinking about this morning, and a couple of years ago, I started doing something that, yep, it's blueberry tea. Wipe the blueberries off my lips. But anyways, having worked in the chemical industry for many decades as a senior research and development manager, I've done something that most academic people haven't done. And that's hired a lot of people, interviewed. Also, having worked for a couple of companies at very high levels, I have been interviewed. And having that experience, I realized I could give some useful tips how to succeed at an interview, either to get into school, say like nursing school, or to get a job. And I don't know, maybe next week before one of the classes, I'll start early. And if you're interested, come on by. I'm going to cut it out of the video because it's top secret stuff. But I can tell you this, over the last 2-3 years, when I've been teaching students that, it's worked. How does it work? I had one student interview for the went to interview for nursing school at University of Chicago, Illinois, Chicago. And she had her interview and they said, thank you, we'll get back to you. And this was in a large building on campus. By the time she walked out the door, her cell phone rang and she answered it. And she said, it was the committee. They said, could you come back up here again? And she wondered, what did I do wrong? And she sat down and they said, you know something, the three of us, and we're 3 faculty members on the committee, the way the story goes, the student told me, and I believe it to be true, is the way you interviewed was the best interview we've ever seen. We're not going to even wait. We're going to offer you a position in our nursing school next semester, next class, if you're interested. And yes, she was. Same thing happened, but not with a school. Chem 170 at my other school's student, I taught what I'll be teaching you. And she was interviewing for a job. I think I always pronounce this wrong. Her training was in phlebotomy, dealing with analyzing blood. And at a hospital, they had an opening, and she went there to interview for it. And she followed my tips. And it was like about 3:30 in the afternoon. She had her interview or ended her interview and got home. About 6:30 at night, the person who interviewed her, the hiring manager, called her and said, you know, I thought about you and that was the best interview I've ever seen. Would you like this job? And she said, of course. So the skills I'll teach you because of my experience help. It's optional. And with that, it's time for a break. So come back in 5 minutes. Don't forget, it's International Chem 1211. Leave your webcam on during the lecture. And thank you for all of you who've done that. I get to see real faces. I'll see you in 5. Time to start. All right. Let me remind you again, don't forget, Handon Labs, you lose 10 easy points if you don't. Also, don't forget, I would highly recommend all of you start working on, if you want to, your extra credit project. Because remember, it's like getting, yes, 10, 10, 10. Oh, wait, yeah, I still have 10 fingers, 10 points. So I would highly recommend you do that. All right, let's get back to acids and bases. Remember, Bronsted-Lowry acid, proton donor. Here, take my proton. Bronsted-Lowry base, proton acceptor. Give me your protons. Now, it turns out, as in life, not all acids and bases are the same. And we have what's known as strong acids and weak acids, and strong bases and weak bases. Now, I'm going to shut the switch. Will this be on a test to the off position? But this is something good to know for the rest of your life and also other classes. A strong acid is a substance that transfers nearly 100% or very nearly 100% of its protons to water. And what do we mean by that? Oh, see equilibrium on whiteboard. Dr. White's going to get lazy and just write it here. Here we have an acid, HA, and if it's a strong acid, the equilibrium is like that. Everybody see the big equilibrium arrow and the small little one? And that means very little goes to the left, and it goes like this. Whoops. Oops. Now this is an equilibrium, but it's almost 100% this way. And strong acids are HX. Oh, by the way, Dr. White did a, and I'll knock that off. I should have. HXX in organic chemistry is a halogen. I won't ask this on a test, but that means HCl, HBr, HI, and a very dangerous acid, HF, are very strong acids. Other strong acids, again, switches off, but nitric acid and sulfuric acid are very, very strong acids. Now, if you were taking my organic chemistry class, which I no longer am allowed to teach at COD, but I teach at ECC, I would show you the chemistry, how strong acids break down your skin to amino acids and really destroy your skin, which is why you never want to get acids on your skin. Strong acids. Now, there's strong acids and they're weak acids. And the weak acid in water hardly goes to the right and stays to the left. Again, switches off, and this would be a weak acid because very little goes in this direction. Example that is acetic acid. And this plus water is vinegar. And that's why you can use vinegar in cooking, because if it was a strong acid, you and all the people you cook for would be in the hospital. Don't do that. But vinegar you can. Another one is citric acid. And this is an acid, and this is found in lemons and limes. The more citric acid, the more tart that is. weak acids have a very tart taste to them. And, oh, I'm going to get you full screen on this, everybody. Hold on. First of all, I'm going to do a whole, going to look at your reaction. How many of you have ever done shots of vinegar? Nobody does that because it's pretty sour. Now, how many of you ever bit into a lemon and you go, "Ooh, is that sour?" Or somebody makes lemonade and puts too much lemon in there and go, "Oh, is that sour?" That's because of citric acid. Your body has a way, Mother Nature, certain things that are weak acids, it tastes sour. Now, bases are bitter, but I'll come to that later on. So think about it. In a number of cultures, we have sweet and sour dishes. And one of my favorite is sweet and sour pork, not the American version, the real Asian version, which I can get at Chef Ping's. And they call it Asian style pork. And it's really sweet and sour, but the Americans like it super sweet, very little sour. The Asian, it's about 50-50. It's got a good, ooh, that's got a good kick to it. But anyways, how many of you have followed the trend in candy for children in the last 5-10 years where they sell the super sour candy? And it seems like kids like the more sour something is, the better they buy it and like it, which Dr. White doesn't like that stuff, never does. And what they do is they just put more citric acid in. Did they squeeze it from lemons or limes? No. Organic chemists have taught how to make citric acid in the lab and then in a chemical plant. And if you want 20,000 pounds of citric acid delivered to your plant, you've got the money and credit, you can have that done by next week. So remember, weak acids are sour. And why is a lemon different than a lime? Well, lemon has more citric acid in it, and that's why it tastes more sour than limes. By the way, Dr. White loves limes, and I don't make that much lemon juice, but I do make a lot of lime juice. If you've never made limeade, it's good. Offshoot of that is 7-Up. Now, switches off, we can have strong bases, and strong base here again, we have an equilibrium, and strong base, the equilibrium is mainly to the right. And two examples, again, switches off, is sodium hydroxide and potassium hydroxide. And their own old name was, you don't have to know, but lye and potash. And weak bases are this example, sodium bicarbonate, are weak bases, and you should know the structure of sodium bicarbonate, NaHCO3, it's in baking powder. And you can use baking powder in various things. Why? Because it's safe, it's a weak base. If you use sodium hydroxide, which you shouldn't, other than there's one area which they do, but if you use sodium hydroxide in a recipe, guess what? You're going to be in the hospital, and anybody else who eats it is. Now, there's one exception, and that's on pretzels. You know how they get the shiny outside? They treat that brownish color, they treat pretzels with sodium hydroxide, but then they wash it off real good so you don't get sick. Dr. White likes pretzels, but other things I like better, like Lay's potato chips. Be quiet. now switches off. You could have mono, di, and tri. Mono in chemistry means 1, di, 2, tri, 3. Protic means proton acids, and they can supply mono, like HCl, only supplies 1, diprotic, sulfuric acid has 2 acidic protons, and triprotic, like phosphoric, has 3. And I just thought I'd do it. In poly, you can have many. And I showed you acetic acid, but anyways, that's it. All right. Switch is still off, but I'd still like to introduce you to some important stuff. And that is the acid dissociation constant. Now, if we look at this equilibrium, and hold on, I haven't done it all day. Thumbs up, people. Can you see acid dissociation? Thank you. Now, normally, for an equilibrium like this, you would have KEQ equals concentration of the hydronium ion concentration, this anion divided by the concentration of the acid and the concentration of water. But it turns out in any solution, this is going to be very large. Tremendous. And that means this number is useless. So what chemists said is, well, if this is very large, let's just eliminate it. And they did. Well, it's no longer an equilibrium constant, so they call it Ka, the acid dissociation constant. And that's where it's like the equilibrium, but you remove the water. And again, switches off. And the same thing is true for base ionization. And here, again, because of the contribution of water to the concentration of KEQ would be so big that the number would be meaningless. Any acid or any base you wouldn't see a difference in the KEQ. They took the water out. Well, Dr. White put some water in, me, and came up with KB. And this is the base ionization constant. Now, why do Ka and Kb? Because the larger Ka is, the stronger the acid is. The larger Kb is, the stronger the base is. Again, switches off. All right, if I had a dial that I could turn to 10, I've just turned it to 1,000. Hint, hint, let's talk about something very important. One of the most important concepts I can teach you in chemistry. I guess that's important. And that is the dissociation of water. Water is a very amazing molecule, H2O, and it can react with itself. It's in equilibrium. Everybody see the dissociation constant on their screen? Thumbs up, people. Thank you. All right. Now, water reacting with itself in equilibrium gives the hydronium ion and hydroxide ion. Water in equilibrium gives the hydronium and hydroxide. And if you notice, no, it's not your eyes. That is a very tiny arrow on top and a much larger one on the bottom. That because the equilibrium stays mainly to this side. Very little goes to this side. And that's that. Now, it's an equilibrium. If we were to do the equilibrium constant of that, let me go up here. it would look like this. And remember, I told you the concentration of water is very large. And now you've got it times itself, which is even a larger number, which makes this number totally worthless. So what did chemists do? Just like with acids and bases, they said, let's remove this. And they did. And they came up with the ionization constant of water, Kw. Notice it's named after me, Kenneth White, Kw. No, I wish it was. But every time I see it. And the ionization constant, and by the way, it's time for Dr. White to be subtle. All right. The ionization constant, by definition, is the concentration of hydronium ion, H3O plus, times the hydroxide ion. And at room temperature, 25 degrees C, it's 1, or really I should have here 1.0 times 10 to the minus 14. And that's Kw, it's the ionization constant of water is that. And the very small number tells you the equilibrium of this is mainly to the left. And know this. Now, let's try something. Oh, come on. There we go. Everybody see that on the screen? If the hydronium ion concentration, H3O plus in brackets, remember putting something in brackets, concentration, moles per liter, is 1.0 times 10 to the minus 10th, then what is the hydroxide ion concentration? So we're trying to figure out this. We're given this. And you know this. So if we start with this equation, by the way, switch is full on now. We're solving for hydroxide. Oh, we've got to get rid of H3O plus. How do we do that? Divide by it. Anything divided by itself is the number 1. Oops, what did I do that for? No, I had too much tea this morning. So whatever we do to one side, we have to do to the other side. And this cancels out. So now I'm left with hydroxide, which I'm trying to calculate, equals 1.0 times 10 to the minus 14th divided by the hydronium ion concentration. I took the time to figure that out up here. So I can now replace this with this. And now Dr. White doesn't need a calculator. Quick thing. When you have 10 to the A divided by 10 to the B, that's the same as 10 to the A minus B. But you can also use your calculator. Notice 1 divided by 1 is 1.0, and this would be 10 to the minus fourth. And that's your answer. Let's do another one. On test number 4, I will give you the following. And you know something? I'm going to let you try this one yourself. What would be H3O plus concentration if the hydroxide ion OH minus is equal to 1.0 times 10 to the minus 2? And thanks to all of you who are turning on your webcam, making Dr. White a very happy camper. And yes, when I was young, I went to camp. That's where I learned one of those most famous songs campers all know, 100 bottles of beer on the wall. Well, that brings me back decades ago. Ouch. Now, one of these days, I'm going to bring in a recording of game show music so I could go dun, 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 dun. Nah. Oh, I see a question. Oh, I see an answer. All right, let's get moving. Hopefully everybody's done. Let's look at the question. And if we're something on a test, it'll be something like 5 points. And that is, if the hydroxide ion concentration, OH minus, is 1.0 times 10 to the minus 2, then what is the hydronium ion concentration? So this is what we're trying to find. We're given this. And you're also given this. So here's where we start. Oh, I forgot to ask. Does everybody see my whiteboard? Thumbs up, people. Thank you. All right, now, what do we want to solve for? Hydronium. How do we get this alone on one side? We divide by whatever we want to get rid of. In this case, hydroxide, OH minus. Because anything divided by itself is the number 1, which means it's gone. So I'll divide by hydroxide. Whatever I do to one side, I have to do to the other, and I did. Now, anything divided by itself becomes the number 1. And now I have the hydronium ion concentration equals 1.0 times 10 to the minus 14th divided by the hydroxide ion concentration. And I took the time to read the problem, so I know what that is. So I can put that in there. And if you take your calculator out, and Dr. White can do this in his head, it's this number, and that's your answer. Now, the question you all should have in your head right now is, so what's so good about hydronium ion and hydroxide ion concentration? Why are we figuring these things out? And that would be a good question. So I better answer it. And when we talk about acids, bases, we have certain definitions that you should know. Oh. I see a question. And the answer, Kelly, is, of course, I have a instant replay request. So let me know when you've copied it down. Oh, tonight at midnight, I'll be giving speed note-taking lessons. No, I won't. Got it. You're welcome. All right. How many of you have ever heard someone say, ooh, you know, the context of your stomach is acidic? Or have you ever heard somebody say that's basic or that's neutral solution? What does that mean? Well, it turns out in our daily life, that's an important concept. Switch is full on. What is an acidic solution? That's a solution in which the hydronium ion concentration is higher than the hydroxide, and it's invisible, but now I'll make it darker, hydroxide. So when you have an acidic solution, hydronium ion concentration is greater than hydroxide. By the way, your stomach is acidic. The liquid in your stomach is acidic solutions. One, because your body makes hydrochloric acid and secretes it into the liquid in your stomach, the water. And that's HCl, hydrochloric acid, is a very strong acid. And time for an observation from Dr. White. One of the great, amazing things I think about in our life is the fact that I have and you have cells in our body that manufacture, produce hydrochloric acid. That's amazing. And I still think it is to this day. And I've known it for a long, long time. And now you do. And it's acidic. Your stomach is acidic because there's an acid present, and the hydronium ion concentration is greater than the hydroxide. Now, basic solution is the opposite. The hydroxide, you can't see it, but I'll make it larger, concentration is higher than hydronium. And you should know that for a basic solution down here, the hydroxide concentration is greater than the hydronium. Now, that's sometimes called an alkaline solution. When hydroxide is greater than hydronium, instead of saying it's a basic solution, people will say it's alkaline. And how many of you have heard of alkaline batteries? And that's because in the battery, the hydroxide ion concentration is greater than the hydronium. Bet you never thought I'd talk about batteries in this class, and we'll talk a little more about it too. Now, if it's greater than hydronium hydroxide, it's acidic. If the hydroxide is greater than the hydronium, it's basic. What happens when they're equal? And we call that a neutral solution. So when the hydronium ion concentration is equal to the hydroxide, we call that a neutral solution. So let's recap. SOLN is shorthand for solution. This is something you should know. When the hydronium ion concentration is greater than the hydroxide, it's an acidic solution. When the hydroxide is greater than the hydronium, it's basic solution. And finally, when the hydronium ion is equal to the hydroxide ion, it's called a neutral solution. And a lot of your cosmetics are neutral solutions because if it's acidic or basic, it will irritate your skin. How many of you want to put hand lotion on your skin or something on your face and all of a sudden see it red and blotchy? I would hope nobody, or irritated. And that's why, but you didn't think about it, acids and bases are important and things you put on your body. Now, if you go back to my calculations I just showed you, well, you got to look at, well, if the hydronium ion is 1.0 times 10 to the minus fifth, and a hydroxide ion is 1.0 times 10 to the minus ninth, is that acidic or basic? And you start thinking about that, and you say, oh, I'm getting a headache. That's not easy. So it turns out some chemists came up with a better idea that doesn't give you a headache. And that is called pH. How many of you have ever heard the term pH? I think some of you might have. And the pH concept, there's a scale called the pH scale. I'll never ask you what is a pH scale, but the pH scale is a scale of small numbers that's used to specify the molar hydronium ion concentration in an aqueous solution. And by definition, you should know, and this is probably one of the most important of the important things I will teach you this semester. pH equals minus the log of the hydronium ion concentration. This I will give to you important information. Now, can you guys keep a secret? Shh. It's time for a Dr. White gift. Now, how many of you are comfortable doing logarithms on your either calculator or slide rule? Dr. White is, but most of you aren't. So here's my gift to you. If the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. If the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. And that I will always give to you that way, that this is 1.0. If it isn't, you got to pick up your calculator and figure it out. So that makes your life easier. Everybody see on the whiteboard? Thank you. Thumbs up, people. If the hydronium ion concentration is 1.0 times 10 to the minus 4th, then what is the pH? And I could have put down what's the pH of the solution. How do you do that? Well, first of all, what are you trying to find? pH. And by the way, pH is small p, capital H. They're not both capitals. And we're trying to find a pH. And the hydronium ion concentration is 1.0 times 10 to the minus 4th. So how do you proceed? pH, and this will be given to you in important information. Years ago, I used to make students memorize this, but I no longer do. pH equal minus the log of the hydronium ion concentration. And for this problem, we took the time to read the problem. It's this. And remember, this I won't put on, but you better remember, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. Well, in this case, x is 4 as 1.0 times 10 to the minus, therefore the pH is 4. And that's how you do pH. That's my special little gift to you. Or actually, it's quite a big gift. See what a nice guy I am? I'm gonna let you try one. If the hydronium ion concentration, oh, this is an ugly looking H3O. Let me fix this up. That's better. Is equal to 1.0 times 10 to the minus eighth, then what's the pH of what is the pH of that solution? Your turn. And when you're done, give me a thumbs up. All right. Dr. White sees a lot of thumbs, so I better get to work. What are you trying to find? pH. What are you given? This. What do you also know? This. pH equals minus the log of the hydronium ion concentration. And this is, in this case, and therefore, if you did the calculation, the pH is 8. Now, you might be asking yourself, all right, so whoopee-doo. I don't know if you say whoopee-doo, but why? Because the pH tells us something important. The pH is only from 0 to 14. The lower the pH, the more acidic solution is. The higher the pH, the more basic it is. I will be going through this on lab tomorrow and Friday. For those who have lab tomorrow or Thursday, Friday, I'll do this. And let me show you one thing real quick. We'll come back to this on Monday in lecture. pH scale. It goes from 0 to 14, never less than 0, never more than 14. When you have a pH of 7, we call that neutral. That's when the hydronium ion concentration is equal to the hydroxide. When the pH is less than 7, this is acidic. When the pH is greater than 7, it's basic. And I'll come back to this on Monday. We will practice this because these concepts right now are probably the most important things I can teach you for your daily life.